And where does the photo come from? We throw some light at an atom, and it's a little bit like ionization energy, except that instead of removing the energy required to move a valence electron, it's the energy to remove any of the electrons. Okay? So you're just going to keep firing photons at a sample of whatever element it is. And as long as you give whatever electron it is enough energy, it will come out. Okay? And then you can measure the energy of the electron coming out. And you can say, okay, this one, could one of you guys get the door there, please? There's a lot of people in the hallway. Thank you so much, Sylvia. One thing to remember about PES is that what does the x-axis do? The x-axis goes backwards. And the reason for that is that it makes it easier for you to orient your graph. So if you think of the origin as the nucleus, then we have the most tightly bound electrons. Are closest to the nucleus, yes? Why is it that the most tightly bound electrons are closest to the nucleus? Pardon me? Yes? Absolutely. Their R value is the smallest because they're in shell number 1. Okay, so the R value is the smallest, so the coulombic attraction is the greatest. Okay. The R value is the smallest. Also, what's their Zeph like? Now we're not looking at an outer electron. We are looking at an electron that is, if I've got my nucleus here, I'm looking at an electron on shell number 1. So are there any shielding electrons? Let's just say we've got that. Are there any shieldings for the electrons? I suppose I should have drawn 2 of them in shell number 1. No shielding electrons. Okay, so again, that's another reason why they are held most tightly, because if you went out to the next energy level, you'd be like, oh, these guys out here are held less tightly because they are also being repelled by the 2 core electrons. Yes, they're both further away and there is shielding. Yes? Probably because they're pushing inward. That'd be my guess. I don't know that for sure. I wouldn't bother explaining it like that. I don't think anyone will ever ask you to explain it. Quite frankly, probably what they're going to do is they're going to ask you questions like this. What element is this PES spectrum for? You know what I mean? That's the kind of question you're going to get for PES. So we have 4 peaks And that tells us that we have 4 occupied whats. What does each peak represent? A subshell. What does the height of the peak represent? The number of electrons in that subshell. So very often, one of the things they'll ask you which element does it represent? You just need to write out the electron configuration and then figure out who that element is. So here we have 1s2, 2s2, and then this next peak is 3 times higher than that, so that would be 2p6. Okay, it contains 6 electrons instead of 2. And then we have 3s2. Now, you could go through and you could do all the fancy stuff, or you could say, I am in row number 3 because it's 3s, right? And the s's match their row number. So I am in row 3. 1, 2, 3. I am in the S block. Yes, so that means I'm in one of these two, and I'm S2, so it's 1, 2. So that is magnesium. Did that make sense? Okay. So as long as you can find your last electrons, you're good to go. Okay. Shall we try B together? Why don't you guys try B on your own, and then you can check your answer with me. Okay. Whoa. I feel like there's something wrong with this one. This feels like an excited state to me. Okay, well, let's find out. Oh, what does the answer key say for this one? This one's making my head hurt. Goodness, what is happening here? Yeah. Okay. Hang on, that's not the one I want. I want the third one doesn't make sense. This one. The third one doesn't make sense either? That's just great. I think this is something that I grabbed from somewhere. And maybe I did not vet it well enough. It was new for this year. So, okay, let's find out. What do we got here? This is 9.4b. All right. Oh. Yeah, you know what? This is just wrong. This is just wrong. Yeah. Bye-bye. Okay, let's try the third one then. I need to fix this. Fix. Yeah, and I need to fix this one because it's missing its 1s subshell. Oh my God, okay. But let's just assume that this is our 2s and our 1s is over here somewhere. then this one would indeed be 2p6. Oh, yeah, this one is just, oh my God, this whole thing is just making my head hurt. Okay, so those ones are gone. Do you want to do D? D looks good. Yes, do D. Good Lord. Okay. Who is D? We got a 3p1, so that means we're in row number 3. Our last electron is in the p block, so that means we're over here, and it's 3p, so this is row 1, 2, 3, 3p1, so that is aluminum. Okay. So other than the fact that we have some incorrect stuff in here, my apologies. Like I said, it's a brand new resource. I just stole it from somebody this year. Well, that's kind of dumb given that they just gave you aluminum. We'll let you answer that sometime in the future. How about you try number 4? Try number 4.
It's the same thing.
But it's for potassium. You don't need to know the exact numbers. You just need to know kind of approximately. So we're going to start out with our one S2.
Does it matter on like what side of it, like the left or right? No, it doesn't matter.
What?
Does it matter if it's shifted side to a lot of different?
It says, pay attention to the relative heights. Exact values for binding energies are not required. So as long as you're like, here's my 1s. When I go to shell number 2, it needs to be significantly less energy than my shell number 1. So shell number 2 is going to be over a significant amount. So here's 2s2. And then we have 2p6. It's in the same shell. So 2, 4, 6. So it's going to be quite close because they're both shell number 2. What's our next subshell? 3s. So should it be close or should it be a little bit further? A little bit further. 3s2. 3p6. 2, 4, 6. And then potassium, what is its last electron? 4p1. So again, because we've gone up an entire shell, 4s, I'm sorry, 4s1. Yes? Honestly, I don't think they're going to get you to answer questions where you have D's on your subshells. That's my bet. Yes, it makes it very confusing. And I have yet to see one on an AP exam where they have D's in there. So let's just go with this. Okay? So we're basically only going up to calcium, probably. Okay? I don't think they're going to ask you to go past calcium. Who is number 5? Just in case anyone was wondering what it was, Tony knows the answer. And indeed it is phosphorus. And if you're like, how do I know it's phosphorus? Well, we go over to our P block because our last electron are in the P3P section. So row 3, 1, 2, 3, subshell, and we go across 1, 2, 3 because P3, and we get phosphorus. I don't care if you draw the Bohr diagram for it, whatever. Which peak represents the 2s subshell? Yeah. The peak at what? 18.7, and you would say megajoules per mole. Now with PES, what we're doing is we're going to fire enough energy at the atom. We're going to fire photons of a particular energy, and that energy is going to be enough to remove this one and all the ones that are small, have a smaller binding energy than that. Yes? And if you remember, if you are trying to kick the ball out of the pit, you need a minimum energy to get the ball out of the lowest part of the pit. Yes? So you need that ionization energy to be enough energy to get the electrons out of the 1s subshell. Yes? If the energy of the photon is more than that, you will kick the electron out. What happens to the excess energy? It's just kinetic energy, and it will just cause the photon to keep moving. Okay? So if I gave it exactly the right amount of energy, if I needed 15 kilojoules to get that electron out, and I gave it exactly 15 kilojoules, that electron would go out, and what would it do now? It would just stop. It would do nothing. Yes? But if I gave it 15 kilojoules, if I gave it 16 kilojoules, it would go out, and then it would keep going a little bit. Now, what if I had an electron that was further from the nucleus? Right? Now I only need 9 kilojoules to get this one out, but I give it 16. Right? So it's going to come out, but it's going to be traveling faster. So on this particular one, this electron gets kicked out and it moves the slowest. The first one. And that's because it requires the most energy to get kicked out. So there's less leftover energy to make it move. So that's this one here. It requires the most energy, so there's less leftover energy. Who's going to be the fastest electron? Electrons in which subshell? The 3p. So these electrons are going to be the fastest electrons after getting kicked out. They're furthest from the nucleus. Therefore, they require the least energy to be removed. And if they require the least energy to be removed, they will have the most leftover energy to make the electron move. So a key idea in that is that all the electrons are given the same amount of energy. Okay, we only have one wavelength of photon being shot at them, and it's enough to get all of them out. Okay, it's more than enough to get all of them out. Yes? Only one energy of light is shot at the atom. Those photons of that energy will have enough energy to kick out all of the electrons. So does that make sense? Because they've got, I mean, I know I haven't really answered this question, but this question is the greatest velocity after ejection is here. So everybody gets the same energy. The ones that are furthest from the nucleus are going to move the fastest because they have the most left over, because they required the least energy to get kicked out because they are furthest from the nucleus. Yes? Nope. Not multiple, well, I mean, all of these are going to involve multiple photons, but not photons of different energies or different wavelengths. They'll always be all the same. No, you're always dealing with a sample because it's always megajoules per mole, right? So you're dealing with a sample. Yeah. How many valence electrons does this atom have? 5. We're good? The ones in the 3p, or in the, sorry, not the 3p, in the three shell. Shell number 3, these are our valence electrons here. Because our core would be neon. Can you guys try number 6? See if you could write a formula and then plug in some numbers. Okay? I guess I should write binding energy.
Is it not ionization?
It is. You could write it that way, but whatever. Does this formula make sense? Before you just copy it down, think about it. Does it make sense to you? Basically, what this question is saying is that we need 2.5 electron volts to detach it. Yeah? And after it's detached, it also has an extra 2.0 volts of kinetic energy. So how much do we have to throw in to detach it and make it move? Right? We're detaching it and we're making it move. Yes. Yeah, binding energy is same as ionization energy. Yes. Electron volts. EV is an electron volt. It's just a unit of energy. What do you guys think about number 7? Could you do number 7? Sorry, yes. What's binding energy? It's the amount, it's the energy, it's essentially the ionization energy for a particular electron. Okay? Let's just write that down here. Binding energy. Now, the reason I think they're using binding energy rather than ionization energy is because ionization energy is the energy required to remove a valence electron from a gaseous neutral atom. So it is like ionization energy, but it is not ionization energy because you're not just removing the outer one. It can be any electron. So it is like ionization energy, but for any electron, not just for a valence electron. Okay, so if you were talking about the valence electron, the binding energy and the ionization energy would be the same. Yes.
Oh, so it's just the first line.
Yeah. Ionization energy literally means if I have a species and I take off the outermost electron, that is the ionization energy. Binding energy is for any electron. There might be outer electrons, but I'm removing this one. Yes? Yes.
Oh, but that wouldn't be any ion.
Yeah, so that's not like first ionization energy, second ionization energy, because you would need, in order for this one to be an ionization energy, it would be the ninth ionization energy? Do you know what I mean?
Oh, yeah.
And you would have to remove those 8 outer ones first. Yeah?
So how do you find gas? It's shooting the light on that is probably exactly what enough to be affected, wouldn't it?
So it's got enough energy to remove this one, which means that it also has enough energy to remove this one because this one requires less energy. You have thousands and millions of photons being shot at that thing, okay? And you have thousands and millions of different atoms. Each atom is it's just going to randomly strike any electron in there. Yeah? So the photons strike a random electron within the atom. That electron comes out. If it was one of the outer electrons, it's moving faster. And that's why it gets detected as being at a different binding energy. They have like a machine that can translate that into the binding energy. Okay. The ones that move slower are the ones that have more binding energy. How are we doing? Are we feeling better about PES? Good. Okay. Now, we've sort of done most of 9.4b, so I think probably for tonight, you could go home and do 9.4c. Yes? Pardon me? Oh, yeah, we could do question 7, yeah, before we move on. Yeah, I meant to do that, sorry. Circle the peak on the following PES spectrum for the electrons that are experiencing the strongest effective nuclear charge. If you have the strongest effective nuclear charge, you are held the most. The most loosely or the most tightly? The most tightly. And if you are held the most tightly, you have the highest or the lowest binding energy. You have the highest binding energy. Where do we find the highest binding energy? On the left or the right? On the left. So the highest binding energy is going to be here. And if you wanted to explain why, it's because those are the which electrons? Those are the 1s electrons. Therefore, they are closest to the nucleus and experience no shielding because they are inner electrons. They're closest to the nucleus, therefore the Coulombic attraction is high because the Coulombic attraction is proportional to 1 over r squared, where r squared is the separation distance. They also experience the highest effective nuclear charge. Because there are no core electrons to shield the 1s electrons from, there are no electrons closer to the nucleus than the 1s. They experience the highest Zeph because there are no electrons closer to the nucleus than the, I guess I should write 1s like that so it doesn't look like is. The 1s, so the 1s electron experiences no shielding. My ribs are doing weird things. They don't want me to breathe. What is wrong with you? Anywho, good times. Getting old is so fantastic. You can just be standing there and your body all of a sudden is like, I'm going to cramp up on you. I'm just standing. I'm not doing anything. I rolled over in bed once and I had kind of a squashy mattress topper. And so I was on my stomach, and as I was rolling over, my kneecap got caught in the mattress topper, and so it kind of slid to the side as I was rolling over, and it took me 3 months of like resting my knee to like get over them. Like I rolled over in bed. Getting older, not necessarily worth it. Anyway, are we feeling good about that? Okay. And nobody has any questions, really, for sure, from the atoms review? Nothing? We're good? Okay, cool. In that case, we are going to go to periodic properties again. And we are on 10.2a, which is page 43.
Do we need to do this on the test? Is it the solution?
Huh?
Is it the solution?
It is, but you should get used to like doing things that are not just within a unit, because AP.
Is it like on the test?
No.
Just
Should you be able to do it? Yes. Is it a good review? Yes. Hi. Yeah. Page 43 in your green book. What's up? Electron affinity stuff, yeah?
It's so confusing. I looked at it, I gave it a try, and I looked at the answer sheet, and I was so off, and I just gave up.
Okay, which ones?
8 and 9.
8 and 9. Okay, let's take a look at 8 and 9.
None of it makes
Place the following elements in order of increasing electron affinity. So we have tellurium. This is page 42. So we have tellurium, bromine, sulfur, potassium, argon. So tellurium, bromine, sulfur, potassium. 8 was fine, so I'm doing a question.
No, I don't understand it.
Okay, so we're doing 8. Okay. Potassium and argon. Okay, so argon is a noble gas. So it'll be the least. Okay? So we want increasing electron affinity, so argon is going to be our least because it is a noble gas. Are we good with that? Okay. Our greatest electron affinity should be at the top right of the periodic table, yes? So we have tellurium, bromide, and sulfur. Tellurium, bromide, and sulfur. I would say sulfur. What?
We're just going with DBRS.
I would go S,
Also K.
BR, TE, and then I would have K. How well do alkaline metals accept electrons? Not very. So I could just go, those only form cations. These guys over here all form anions.
Also, we're going to pay for it.
Huh? I would put K after argon, yeah.
And then you go tellurium, bromide, sulfur.
Hang on. No. Sulfur, bromide. No, yeah. Tellurium, bromide, sulfur.
What is the answer?
Yeah, what does the answer key say? That would be my best guess. And before we get too wound up about this, remember, how often does electron affinity come up on the AP exam?
No.
Never. So, you know.
That is not right. That is definitely not right. AR is right. E is right. S and BR is wrong. Oh no. Okay, I probably should have been young. I don't know. I should have been noble gas.
Okay, so we were good. We were good other than this one. So apparently S and then BR. I'm guessing. I don't know why. I wouldn't worry about it. Yes. Which would have the smallest electron affinity? So we have.
It would be noble gas, right?
Oh, it would be the noble gas, I would imagine. Yeah.
You said it was not a noble gas.
Oh, that's interesting.
Wait, did it say RB? Yeah, it said RB. I don't know why it said RB. Video.
Oh. Well, let's just take a look and just see what the. Yeah, no, it should be the noble gas. The answer key's wrong. Okay, so for this one, we need to fix the answer key. For number 7. And then decreasing electron affinity. So our most would be fluorine, because fluorine is small and it has a high Zeph. Yes? It is the smallest and it has the highest Zeph. Now the rest of them, we've got metal, metal, metal. So I'm going to assume it's going to be S because S likes to gain electrons to become S2 minus, yes? And then we have tin and lead. Well, out of tin and lead, tin is going to be better than lead, right? Tin is better than lead. And cesium is way at the bottom left of the periodic table, so I would say it's the worst. Why? Because it has the smallest Zeph and it's huge. Because CS is at the bottom, so it's big. And it has a Zeph of only +1. Okay, hang on a sec. Okay. Okay, so I mean, no. If I can't do it, are they going to expect you to be able to do it? Did you get it kind of close? Right? Because we've got, I mean, it turns out that lead is less than cesium, but I don't know why. Can I tell you how unimportant this is and you guys are wasting a lot of time on it? Yeah? Are we okay with the important bits, which would be this? Are we okay with those first three? Are we okay that lead and cesium are going to be down in the bottom somewhere? Good, done. Close enough. Is anyone going to ask you that actual question with vague things where you can't really figure it out? No. Obviously, these questions are a little hinky, and I would like to fix a bit. Yes? So don't get wound up about it, though. Don't get all like, oh my God, I don't know it. I don't understand it. I just give up. Oh my God. No, it's not worth your stress. It's just not. Okay. What do we notice about our ions compared with our atoms? Why are the cations all smaller in radius? They lose an electron. Not only do they lose an electron, but they lose electron, which does what to their valence shell? It empties out the valence shell. So the cations have one less occupied shell than the neutral atoms. One less occupied energy level, right? We get rid of the 3s. And now we only have the 2s, and that's why they're all smaller. Is good? Okay. Why do anions get bigger? They gain an electron, which fills up their valence shell. And if you're adding another electron into an orbital, what did you get? You get more electron repulsion, We've done nothing to Zeph. We've done nothing to the number of occupied shells. So the only thing we can be looking at is electron-electron repulsion. Is good? Okay.
Wait,
Yes.
if you fill up the valence shell, doesn't that mean all of the orbitals are shielding shells or shielding?
The only shielding electrons are here. They shield the outer shell. The outer shell doesn't shield anything because there's nothing outside of it to be shielded. Does that make sense? Okay, cool. Are we good with that? Okay, so our overall trends, basically, your positive ions get smaller here, and your negative ions get smaller. Why is that? That's because there are more protons than lithium. And what does that do? More protons causes the electrons to be pulled in more strongly. This one is not so much a periodic trend as in like everything goes like biggest to smallest all the way across. It's like if you're comparing, you know, your +1 lithium ion to your +2 beryllium ion, that's the kind of thing you might be asked to compare. You might be asked to compare oxygen and fluorine. Fluorine, again, has more protons than nitrogen or, not nor, sorry, I'm going to put a space there, nitrogen or oxygen. Therefore, it's pulled in more tightly. Therefore, it is smaller. This one is larger. Does that make sense? Okay, cool. Obviously, as you go down, yes. Why are noble gases really small? Because they have the largest Zeph. Yeah? They have the same number of shielding electrons, but they have the most protons. So they're the smallest. As we go down as we go down a group, it's pretty much just like atomic size. Okay, lithium plus, sodium plus, K plus, they all get bigger because there are more occupied shells. Okay, that's all there is to that. Yeah, it just increases as you go down. And once again, we get into the isoelectronic series, which we did talk about before. All of O2 minus, F minus, Na plus, Mg plus, and Al3 plus, those are all isoelectronic. What does isoelectronic mean? Same number of electrons, same electron configuration. And who do these all have the same electron configuration as? Neon, okay? Which is 1s2, 2s2, 2p6. Yes? All of these guys have 1s2, 2s2, 2p6. But the number of protons is 8. Protons is 9. for fluorine. Protons is 11, and then 12, and then 13. So who's going to be the biggest and who's going to be the smallest? Oxygen has the smallest number of protons. Therefore, its Zeph will be the smallest because the core electrons are the the core electrons are the core electrons, whoops. The core electrons are the same. Yes? But the protons increase. Yes? Core electrons are the same all the way down, okay? They're all the same all the way down. And that means that as we go down, Zeph increases. And so they get pulled in tighter and tighter. So within an isoelectronic series, whichever has the highest atomic number, whichever has the highest number of protons, will have the smallest ion size. Okay? Are we good? Okay. I think that's it for this one. So I think you guys could do 10.2b and 9.4c. Okay, so 9.4c is PES. And then this is atomic and ionic radii. And we have 10 minutes left, so you might as well, or like whatever left, you might as well get some of it started. And in the meantime, what I'll do, yeah, you can go. In the meantime, what I'm going to do is I'm going to come around and throw some structures on your desk, and you can also guess what their shape is. Okay, you can use your sheet that you got last day. Is there anyone who did not get a sheet with the molecular geometries? I'll get you one. Yes.
Let's say six.
Yeah, it doesn't. They don't like. So find its shape and its hybridization. Some of them don't have hybridization. I don't know, you look it up. And remember, the little flat things, those are lone pairs of electrons. Trigonal molecular development, these ones do not have. And its hybridization is. Yes. That's not what it is, but that's.
Wait, what is the hell these?
Hi. Is where so are actually You're all in fire. So this is like, whenever you come to work, hello, what have you got? Yeah. How about you?
No,
Oh, I'm sorry. Who's this? There's 1, 2, 3, 4, 5. Make the square. Shut up. So the job is nothing to do with reality. S. Yeah. Yours is T-shape, and there's no.
Good afternoon, everyone. Just wanted to remind those that signed up to come to Mr. Roll 2 at lunch for the second event. All teachers are welcome as well. Thank you. And just one more reminder, Douglas College is here right now in room 200 for anyone who is interested. That's Douglas College right now in room 200. Thank you.
Yes. Thank you so much. Sorry. I really.
I don't know who was here on the day you just saw.
That's possible. Let's look. Yes, you are correct. Thank you for remembering. There you go. Oh, yeah, thank you.
Miss Spence, here's another one.
Oh, thank you so much.
But hi, how come this one is 3D10?
Because you remove the outer energy level first, you remove the highest energy level electrons
I didn't
first.
do them in order that
Yeah.
way. Yeah. Okay.
Yeah.
I get it. And this
So
one too?
you can write it like this, just remember to take out 4s before 3s.
And then this one too. So
And that one, same thing. Yeah.
that's all.
Yeah.
Thank you.
And now that you've done it, you can keep that. Now that you've done it, you'll never make that mistake again. Right?
Ever.
Ever. You'll be like, oh my gosh, those higher energies have to come out first. Electronegativity is not a
Or a variable potential strip happening down.
Yeah. Yeah, so like E equals H. Okay, so it goes. Yeah, it'll get that.
This fence is.
Like, where's your street?
I need a target.
Rose calling me. No, I definitely need a more. I'm sorry. I'm not.
I don't care.
I don't care either.
I let you already see if you need a target. You knew I don't know. You see what